One of the most celebrated mechanisms in the class of mechanisms with transfers is the Vickrey-Clark Groves mechanism. This also goes by the acronym VCG. This is a work by three scientists, Vickrey, Clark, and Groves, spanning over more than 10 years. So we have already discussed the Groves class of payments, which actually came a little later historically. The first thing that came in this class was the Vickrey auction, also the second prize, also known as the second prize auction. It was further generalized by the Clark mechanism, which we are going to discuss now. So VCG mechanism is essentially that form, and Groves later generalized it to what we discussed in the last module. But regardless, they are all credited in this mechanism, the VCG mechanism, which is also known as the pivotal mechanism. We'll see what is pivotal about this mechanism when we discuss the examples. So what is it? Now that we know the Groves class of payments, it's easier to explain it in terms of this hi theta minus I, the function that we have defined to define the payment function for the Groves class. So this pivotal mechanism, or the VCG mechanism, picks this hi theta minus I in a unique way. So what that value is? Notice that we are now trying to take the sum of all the valuations of the agents except agent I. So while we are trying to find out the hi, the function for agent I, this must be the function that does not depend on theta of I, the type of player I. So it is picked in the following way. It is trying to maximize the sum of the valuation of all the players except agent I. So imagine as if player I has been removed from the system. What is the total social welfare, the maximum social welfare that can be achieved without that agent? That is the hi theta minus I function. So with that, the payment is going to be modified to the following. So this is the payment for player I. hi theta minus I comes here. That is the total social welfare without agent I, the maximum social welfare without agent I. And the second term is the sum of the valuation of all the agents except agent I at that efficient allocation. So here agent I was present, that possibly gave a little worse outcome for all the other agents except agent I. So that welfare of the other players is being subtracted out from the maximum welfare that they could have got. So in some sense, you can imagine this payment to be the maximum social welfare that can be achieved without agent I. But those agents except agent I that are getting the social welfare because of I's presence is given by the second expression on the right hand side. So this difference is the net damage, if you want to call it, that player I is doing to the other players. And this mechanism is asking agent I to pay that amount, compensate that amount. So that is one way of interpreting this expression. Now notice that because this is a summation of the valuations of all the agents except agent I, and the first expression here is trying to maximize that, so very naturally this is going to be larger than the second term. So it is quite clear that the payment in the VCG mechanism is always going to be non-negative for all players and for all theta. So which means that we have discussed this property of a payment. This is known as the property no subsidy. So the mechanism designer never pays anybody. It just extracts payments from the players. And because it is no subsidy, if you take the sum over all these payments, you are going to see that the sum will also be non-negative. That means it has no deficit. So VCG payment never runs into the deficit. So that is one way of how we can interpret this payment function. We can also interpret the utility of this VCG mechanism just by rewriting this in a careful manner. We know that the utility of player I will be the valuation of that player under that efficient allocation. So remember that this efficient allocation is just trying to solve the same problem with all the players together. So if efficient of theta I theta minus I is essentially the argmax of all the valuations, so v of a comma theta I for all the players, and that is for a in a, right? That just for a reference. Now we expand out the payment function and we can rearrange. So you see that this part, the second term, has f efficient. So when you take this negative of it, it becomes this sign becomes positive, and that gets added to the first term, and therefore you get this expression, the sum of the valuation of all the players including agent I. And the second term, which is the first term of the payment function, that comes as a negative. So that's the maximum social welfare of all the players except agent I. So you can interpret that the social welfare in the absence of agent I, and this is the social welfare in the presence of agent I. So in some sense, this difference is the marginal contribution of agent I to this system. Because of his presence, what is the social welfare minus when if he was removed, what would have been the social welfare? That marginal contribution is manifested as the utility of player I in this mechanism. So let us discuss some examples and to understand what happens with this mechanism. Let's go back to our favorite example of a single object allocation. There is only one object to be given out, and the type of all the players is the value for that object. If they are allocated, how much they value this object. Maybe it's a painting, and therefore it has some monetary value associated when you get that object. And if you do not get that object, the value is 0. That is the assumption. Now we'll have to find out what is the payment, the VCG payment. Now notice that first expression is trying to find out what is the sum of the valuation when that player is not present. So if you remove that player, and the maximum, so because this object is indivisible object and it can be given to only one person, at most one person, it goes in this scenario, it should go to the player who values it the next best. So it's the second highest valued object. So the first thing to notice is that the efficient allocation should give it to the most valuable buyer. So the person who has the highest theta, the highest type for this object, should get that object in the efficient allocation. But when he is not present, it should go to the individual who values it the next highest. So you can think that this is the second highest value. And when this object goes, let's say player I is the highest valued bidder, in that case, what would happen to this sum here? So sum of all the players except agent I. They are not getting that object. So the sum of the values of all the agents except agent I will be equal to 0. So this term becomes 0 for the when I is the winner of this single object allocation game, and this one this sum is the second highest value. So when you take the difference, it's essentially the second highest value. So that means that the VCG payment is asking the winner to pay the second highest bid. And what happens to the other players? So when you have the other players, let's say I is not the winner, then even if you remove that agent, he is not the highest bidder, so the agent with the highest theta. So here in this sum, there will exist that agent who has the highest theta. So his or her valuation will be coming in this max term. And even in the efficient allocation, if you are looking at agents except agent I, where I does not have the highest value for that object, the same value will show up. So this difference will then be equal to 0. So the interpretation there is that if I is not the winner, his VCG payment will be equal to 0. So that's the interpretation. So when you have the highest, so if the agent has the highest type for this object, he is essentially asked to pay the second highest bid. The people who do not win the object, they pay 0. That is precisely the second price auction. Let us look at one example. So if there are 4 people and their valuations, their types are as follows, then the efficient allocation will be to give the object to the first player who has the highest valuation for it. Now if you put these numbers here, so this should be the sum, so this should be the maximum of all these 3, which is 9, and this will be equal to 0 for player 1. So therefore the payment there is 9, and for all the other players this payment should be equal to 0. That is exactly the second price auction. So that is one example of the VCG payment. Now we have also mentioned that VCG payment is also known as the pivotal mechanism. So what is pivotal about this mechanism? Let us look at this example. So suppose there are 3 players A, B and C, and there are 3 possible alternatives or allocations that can happen. So either the decision can be to build a football ground, which gives different valuations. So this table is showing different valuations for these 3 individuals. So maybe A does not like the game of football at all, so she gets 0 valuation when this ground is made. B is a football enthusiast. In that case, B gets some large amount of valuation, and C gets some moderate, some small valuation when this is made, and similarly for the other alternatives. Now if we apply VCG mechanism here, note that the VCG mechanism comes from the class of gross mechanism. Allocation rule is the same rule which picks the alternative or the allocation that maximizes the sum of the valuation. So if we look at here, we look at this alternative here that gives a total social welfare of 105. Library gives a total social welfare of 120, 130, and museum gives a social welfare of 150. So clearly museum is the winner, so that is the social welfare maximizing allocation. That is also going to be the allocation in the context of VCG. Now we'll have to find out what is the payment that all these individuals make, and that is exactly where this pivotal thing comes in. So just use the expression, the formula that we have already discussed. So when you are trying to compute the payment for player A, so the first term will be in the allocation and the sum of the valuation of all the agents except agent A when A is not present. So if you remove agent A from the system, what will be the outcome? So you know that this will be the sum for this outcome. This will be the sum here, and this will be the sum here, and clearly this is going to be the winner. So therefore 105 is the sum of the valuations of the agents except agent A when A is not present. Now when A was present, the sum of the valuations of the other players was 100. So this difference is going to be the payment that is imposed to player A, and that is going to be 5. Similarly, when you look at player B, so you will have to do the very similar thing. So you remove player B from the system and look at what is going to be the outcome. So in that case, now outcome would have been library. So in that gives the sum of the valuation of all the other players to be equal to 120, and because of his presence, the sum of the valuation, that is this and this, is 100. So this difference is going to be 20. So that is the payment for player B. And similarly, you can find out the payment of player C. If you remove player C, you can see that the outcome does not change. It remains the same, and that is what is happening in the last case. So here the sum of the valuation of all the other players when C is not present is same when he is present. So in some sense, C is not a pivotal player, and that is where this idea of pivotal mechanism comes in. So if a player is not pivotal, that is, his presence or absence does not change the outcome, then in this mechanism he is asked to pay 0. So he is not charged any money. and that is one interpretation of this thing, of this mechanism. The third example is of a combinatorial allocation. So this applies to the cell of multiple objects. Let's say there are two objects and there are four possible bundles using of these objects. Either the bundle could be empty and with no objects, or it can have those objects individually, and there could be a bundle of both the objects together. And the players may have different valuations for these bundles. So here this numbers show what are the values for these different bundles. One assumption that we have already made in the beginning is that when the allocation is empty and the bundle is empty, then the valuation is 0 for all the players. So the understanding of this table is quite evident. We are just using this shorthand notation to denote the same thing as the valuation under a certain allocation when the type is theta I. This shorthand can be used because this is very simple. There is a specific number associated with every individual and an allocation. Now we can find out, so we are going to apply VCG mechanism on it, and the first step is to find what is the allocation. And now here we can see that the allocation is so this social welfare is going to be maximized if you pick these numbers, right? So you give the first object to player 2 and you give the second object to player 1. That is the best allocation. That gives you a social welfare of 15, which outperforms any other allocation, any other social welfare. Now it's the time to compute the payment. So when you remove a player, so let's say we are trying to find out the VCG payment for player 1, you remove that player, and then you can give both these objects to player 2. That is the maximum that you can achieve, and that is going to be the first term here. And because of this, in the presence of player 1, what is the social welfare that is obtained by the other players? So here there is only one other player. That player is getting 9. So this difference is going to be the payment for player 1. And therefore the payoff, because when under this allocation player 1 is getting a utility of 6, the valuation is of 6, and the payment that he is asked to make is 5. So the net difference is 1. Similarly, if you compute the payment for player 2, it is going to be 6, and player 2 is getting a valuation of 9 under this allocation, and the difference is 3. So that's the net payoff under this combinatorial allocation.